All right, I want to do this proof with you because that's going to lead into our new fact. All right, just so you know where we're going with this last part of this unit. All of quiz 2 is what? Dedicated to angles. How to find any type of angle, inside, outside, tweener, whatever. Now what it's going to be dedicated, this last part of the unit, is how do I find the length of something in a circle? Radius, diameter, chord, tangent, secant. How do I find their lengths? All right, so we're moving away from angles and now moving to lengths. And that's what this first proof is going to show you, is something about chords. All right, what's so special about chords and how to find their length? This is not a new proof, by the way. This is a great proof for me to review with you guys. Anybody remember what unit we used to see that statement in? Oh. Where do we see that proof statement? Period 3 now. Okay, keep going. What was the overall theme of that unit that did deal with that and proportions? Matt, Matt saving you. Way to go. Similar triangles. Way to go, Matt. Yes, this is not true unless the triangles are similar. What's our main method? Angle, angle. All right, find me 2 pairs of congruent angles up here so I can prove the triangle's similar first. Give me 1 pair that you see. 1 pair of congruent angles. Any method, Aiden?
CBA and CDA.
Look at you. Nice. I like how you went right for something you just learned. Perfect. Angle B congruent to angle D. Going out to everyone, what type of angles did Aiden just give us? Those are just finished it. What type of angles are those? Inscribed. There we go. Inscribed angles. Where are they both drawn to? Same arc. There you go. Inscribed angles drawn on the same arc are congruent. Thank you, Aiden. I need another pair now. Another pair of congruent angles up there. Whew. All right, let's go right there, Charlie.
CEB and AEB.
Okay, you're going to make me work harder. We can put those. All right, we could have also put C and A in the same statement for number 2 because they're also inscribed angles drawn on the same arc. But hey, I don't mind making our proof a little longer. It makes me look smarter, right? Angle CEB, congruent to angle AED. Good work. And those are what type of angles? Just want to review it, make sure we're good. 12. Olivia, what type of angles? Charlie, just give us vertical. Vertical angles, congruent. And now I have angle, angle. Now I can say the triangles are congruent. So what do I have? Triangle CBE. CBE, then I got to go ADE. By angle, angle. How many of you, again, embarrassment to the math community, putting a congruent sign instead of similar? Get it out of there. Or get out of my room. Now, step 5 is not this proof statement. We had a step in between. Anybody remember what the reason's going to be for this? We identified it with similar triangles, but anybody remember the reason we always put that when I multiply these 2, it's equal to those 2? Come on. Matt, you remember that one or no? Or anybody else? What? Go ahead, Jen. Product of the means equals product of the extremes. But before I write that, I need to have means and extremes. Where did we always have means and extremes in? Zeev? There you go. There's your proportion, right? We always got means and extremes from our proportion. So I need a proportion first before I say the means and extremes are equal. So that's what step 5 is going to be. All right, the triangles are similar. Now we can put those sides in proportion. And how do I build the proportion? From your proof statement. If I'm going to put AE in the top left-hand corner, and you're telling me to multiply it by BE, how do we solve proportions? Cross multiply. So BE has to go diagonal to it, or in the bottom right. And then CE and DE can go in the empty spots. Oh boy, still challenge you. This is not means and extremes yet. Anybody remember why the proportion was true? Anybody remember why corresponding sides in similar triangles were proportional? One more time. Does anybody remember the reason we put to say corresponding sides in similar triangles are proportional? CSS TP, corresponding. Oh, that's why he was saying it so loudly twice. Now you can cross multiply. Now you can cross multiply and say AE times BE equals CE times DE. Product of the means equals product of the extremes. What did we just prove? As far as when it comes to circles, what did we just prove? Something huge you just proved when it comes to circles. What's AEB in this diagram? AEB, what do we call that in a circle? Line segment AEB, that's what in my circle here? Amy?
Chord.
That's a chord, and so is CED. And they are intersecting, and that is when this theorem only applies, when two chords intersect. So that's how I'm going to start this one off. When two chords intersect, okay, so when two chords intersect each other, this happens. But I don't want you to write this happens, right? What is this? What do you call the answer when you multiply? Product, yes, the product. But I'm not doing means and extremes here. I'm going to refer to it to the circle. So the product of their parts are equal. So when two chords intersect each other, the product of their parts are equal. And here's what I mean. I won't put any numbers to it yet, but look. AE times EB, the two parts that it got broken up into, equal CE times ED, the two parts of the other chord. That's what this new theorem is saying. The product of their parts they get cut up into are equal to each other. All right, let's put some numbers to it now. And yes, you don't have to let me know. I know yours doesn't match up with mine. I know what order your problems go in, and I'll match it in a minute. All right, number one, right away. Everyone sees the two chords, and they are intersecting. They have to intersect. All right, two chords intersecting. The product of their parts. You just proved this using similar triangles. The product of their parts. So I need somebody, take one chord, tell me what its two parts are. Take one of those chords and tell me what its two parts are. Amy, one chord. 2 and X. So I'm going to say their product, by multiplying them, is equal to the product of the other two parts of the other chord. So look at the other chord. What are the other two parts up there? One's, 8 and 2.5. So their product. They're equal to each other. That's what you just proved by doing means and extremes. Notice how we're not talking about angles anymore. What are we talking about? Lengths of different parts of a circle. So 2x, that's equal to 20. Yep, I get x equal to 10. Basic, right? Everyone's okay. Are you understanding the theorem when it relates to a basic one? Because you know I'm going to up the complexity of it and the difficulty to an honors level here in a second. We're good? All right, number 2, I know you don't have. Oh, so sad. So sad, students. No diagram to look at. Oh, so sad. Guess we got to draw one. Chords AB and RS are intersecting at E. AB, RS. All right, so everyone's throwing down a 3 on EB, and everyone's throwing down a 16. Sorry, AE. My bad. 3. EB is 16. Great, numbers in a ratio again. We've had exposure to this when we did the arcs before, right? When arcs were in a ratio. So what are you guys labeling RE and ES as? RE and ES, what do we put on those? Shoom, Olivia, back to you today. They're in a ratio of 3 to 4. Yep, you got it. Good work. Good work. Two chords intersecting, product of their parts are equal. Give me 2 parts of 1 chord so I know we're good. 2 parts of 1 chord. Shoom, Thomas, 2 parts of 1 chord. There you go. So I'm going to go their product, 3x and 4x, always equal to the product of the other 2. And what are the other 2 up here? We have labeled. Thomas, back to you. Your problem. 3 times 16. Got it. Oh, now we're going to have a little fun. Who's got the algebra skills from last year? I got this part, 48. 48? Yeah, 48. How about 3x times x? 3x and 4x. This is going to get fun now. Who is going to put their Algebra 1 teacher last year to shame? Who's going to do it? 3x times 4x. What do you think? What do you got for me? Oh, boy. Amy?
12x squared.
You better have that squared at the end of it. Yep, not just 12x, but x times x gives you the squared. Good. Your Algebra 1 teacher smiling. All right, great. What do you do now? Got to get x by itself. What's your next move? We got the 12x squared part. Good job. Now what's next? Come on now. Woo. Good talk. Good talk. Thomas, back to you. What do you think?
Get the square root of both sides.
Not yet. Not yet. I cannot square root both sides unless that's by itself. So you want to give me another move there, Thomas?
Divide by both sides as well.
There you go. Yes. So everyone good? I know a lot of you probably thought square root can only do it if the variable's by itself. Now we can do this, right? Now we could take the square root of both sides. Real quickly, though, because you are honors level, so you should be treated like that. I should get plus or minus 2, right? Like every take the square root, you get the plus and the minus version. Why am I not even going to bother with the negative 2? You plug that in, I can't have a negative length, segment length. That's silly. So I'm just going to deal with the 2. But that did not answer our question, though. Go back up to parts A and B. Find RE and ES. How about RE? Length of RE when you have it? Whoa, there we go. Back to Charlie. 6. And how about ES? Whew, owes me big time there. Ian? 8. Everyone seeing our theorem right now? 6 times 13, 48. Equals 6 times 8, 48. Good check. Good check. Questions, comments, concerns? Oh, you want harder? You got it. Let's do it. Number 3 here. Find the length of the chord, CD. All right, everyone, that chord's 3 centimeters from the center. So plop a 3 on your diagram somewhere. Preferably the chord from the center is 3 centimeters. And the radius is 5. You should put in, knowing the radius is 5 should lead you to 2 more lengths. 2 more, not 1 more, 2 more lengths on this diagram. Yes, it leads you to a radius of 5, but it should lead you also another length too. This radius is 5, so that piece is 3. We should all be putting a 2 there. And we got to find the length of the chord. We're not done with this unit yet. Something's happening in that diagram from a circle fact. Anybody see the circle fact that's being used? Now, I'm not talking about the one I just showed you. One you probably could have used on your quiz yesterday. Chord's getting diameter, perpendicular to a chord, bisects the chord, right? So I know these 2 are equal. All right. I have a problem, though, and I need your help. The fact that I just gave you guys, we just did that angle, means an extremes proof with said when two chords intersect. I only see CD up there. Can we use that fact still? When two chords intersect? I only see chord CD. What am I missing? I see a chord and a diameter, so what am I missing here? It said when two chords intersect.
A diameter is a chord.
Josh, one more time.
A diameter is
A diameter is a chord. So just because it's a diameter, we can still use this fact. Good. And they are intersecting. So that means the product of their parts are equal. Let's start with chord CD. What do I put in for that? What times what? They're both the same, right? Everyone, yeah. You find one, you double it, and I got the whole chord. There we go. It's both the same. Now here's where you need to slow it down when dealing with the diameter. It's still part times part, and it starts at the intersection point. What's one part on one side times the other part on the other side? All right, what are we looking at here? 6. Thomas, back to you. Give me one part here. 2. Everyone's good. Everyone sees that part. Now, when you give me the other part, it doesn't stop at the center. It's the entire other section. Which would do what here, Thomas? Keep going. There you go. Not 3 in there. It doesn't stop at the center. Part times the other part, it gets divided up into. We all good? All right, so be careful when dealing with the diameter. Yep, x squared equals 16. We know it can't be negative 4, so x equals 4. You're not a winner yet. I still need to do what to find the length of chord CD, which is what I was being asked. Oh, there we go. Olivia, you are on fire today. What do I still need to do to find CE? Yes, I do. 8 centimeters. Watch out for diameters. Speaking of watching out for diameters, here's the next one. Do you see two chords intersecting? Yes, hopefully you do. So what I need somebody to do first is tell me the two parts of one chord that you already know. What are two part lengths of one chord that you already know? Gianna, good.
8 and 10.
Perfect. Thank you. 8 times 10 equals, let's go to the diameter now. Diameters are tricky. Can we all agree one part of the diameter I'm going to put in is x? That's one part. Ooh. How about this other part right there that I just highlighted in yellow? How can we express the length of that one now? Well, I threw that 12 in there, right? What's the 12? Radius. Everyone agree that's a radius? And we said this chord was a diameter. The radius is 12. How long is that diameter? 24. Double it. Well, if the diameter is 24, that part of it's already x. How can you express what the other part is going to be? Right? How do you express the? We already know doubling the radius. That gives me 24 for the diameter. One piece is x. Express the rest of it for me then. If it all equals 24. Oh, what do you got for me here? Josh?
24 minus x.
Wow, unbelievable. Way to show you belong. 24 minus x. Oh, we are not done having fun yet with this problem. Oh, you're going to be so sad. 80, no problem. Equals. All right, looks like we got to do a little distribution, the distributive property. 24x minus x squared. No issues yet. This is not one where I can take the square root. I can only take the square root when x squared is by itself. Look, I got an x squared and an x attached, so there's no square rooting here. Get that garbage out of here. How do you solve something like this? Oh, this is going to make me so happy. Anybody? How we're going to solve this? Josh, go ahead, say it.
Factoring.
Say it. Go on one more time.
Factoring.
Factoring, yes. Yeah. A proof and factoring in the same day. Well, I got bad news. You're not factoring this. You guys learned all last year. You don't factor anything unless it's... That's a 0, by the way, if anybody's wondering what I'm doing. That's a 0. Unless it's equal to 0. Convenience would say move the 80 over. I don't know about you guys, but I start sweating profusely if somebody asks me to factor and the x squared's negative. I go nuts. Just sweat pouring everywhere. So I'm not going to go for convenience. All right, I'm going to move the right over to the left side. So move the x squared over. Now it's positive. Move the 24x over. Now it's negative. We never touch the 80, so it stays positive. Equal to 0. Yeah, now it's time to factor. And hey, this is the only type of factoring I've shown you guys this year. I've not shown you any other techniques. You're playing a game right now. What's your game? False. What's your game going to be? No, you can write it. You're just not going to circle. What's the game we're playing? 2 numbers that?
Multiply the 80.
Thank you. Multiply the 80 and add to negative 24. Here we go. What are they? Search. Search. I don't give these numbers for free. I can tell you it's not going to be 80 and 1. Or 2 and 40. Or 10 and 8. None of those I just listed add to 24. So there must still be a pair out here that will. All right, what are those numbers? Anybody have them? Not me, not me, not me. There we go, Josh. Do you have them?
No.
Let's go. You got them.
Oh, I'm trying.
I skipped over it on purpose. 1 and 80, 2 and 40, 10 and 8. Don't work. I skipped over one on purpose. Let the kid work. What do you got?
Negative 20 and negative 4.
All right, I had faith in you. Now you got to take it out of the parenthesis and let me know what x equals. So x equals positive 20 and x equals 4. Here's not my favorite part here, but the awkward staring contest till somebody tells me we're not ready to move on. Zeev, I am geometrically incorrect here. Why?
It can't be 20, right? The radius is 12. The whole thing's 24.
Everyone, if the radius you told me was 12, how can x, which is part of the radius, be bigger than that? Agreed? So yes, 12. All right, sorry, 20. Rejected. I just have 4. All right. Okay, so there's your first circle fact for today. I have one more quick one to end class. I've never seen star before. That's one of them. Never seen that one. Here's your last one. Real simple, easy to understand. If 2 chords are parallel to each other, what do I put on diagrams to show lines are parallel? It's been a while. Arrows, thank you. So if 2 chords are parallel, so if I have, take a look, parallel chords, That's not 11 chords, by the way. That's parallel. Not 11 chords, parallel chords. If the chords are parallel, the arcs in between are congruent. So parallel chords imply congruent arcs. Nice and simple, this one. If you know two chords are parallel, the arcs in between them are the same measure. We'll do the first one together, and I'll leave you alone or in your group to do the last two. So this first one, circle O, chord A, B, and chord C, D are parallel, which means the arcs in between them are congruent. So CA congruent to DB. What's one of the missing arcs, CA? All right, look at the diagram. What do you know about those three arcs? The 80 I gave you and the two congruent ones. What should I know about those three arcs? All three of them do what, Gabby?
Equal 180.
Darn right, because that's a diameter semicircle. Good job. So I have 180 minus the 80 I just gave you, divided into two congruent arcs. So 50 degrees equals arc CA. Okay, by yourself or in your groups, you're on to the next two. I'm just going to write the answers up here. If you get the answers, no issues, you move on in the packet, which is the assignment tonight. Everything's in the packet tonight.